Hello everyone, my name is Dario Tarquini and I work as an intern at Exemplary Energy. In today's presentation, we'll be looking at our work on improving Australian weather and climate data services and how these tools can be used to improve energy efficiency outcomes through building control and design optimization. We'll start on a bit of background on these tools to then move on to some more recent developments and applications of the sort of data that we provide. And we will conclude with some future development of motion modeling and cloud cover that we intend to incorporate into our data. So firstly, let's dive into a bit of background. This weather and climate data is used a lot throughout the industry by developers, both for residential and commercial buildings of all types. For example, someone might be familiar with the Section J of the National Construction Code, where for demonstrating compliance, you can develop a computer model of the building, and then you apply the relevant local climate data to evaluate the performance. And then what you do is comparing the model to another model that was built using the deemed to satisfy energy provisions in the NCC. And if you can demonstrate that your building is more efficient than the deemed to satisfy building, then your design can be deemed to comply. And so in order to demonstrate energy efficiency compliance, both residential and commercial applications use what we call the representative meteorological year or typical meteorological year. They are hourly dataset of a range of climate and weather elements such as dry bulb temperature, humidity, wind speed and direction, and solar radiation that have been compiled to represent the typically hour profile of weather for 12 months or a period of 8,760 hours. When we apply the climate data to a building energy model, it is possible to evaluate the impact of the hourly data on the building's heating and cooling consumptions over the course of the typical year. To do this, the raw data is drawn from meteorological observation. They usually come from the Bureau of Meteorology sensor networks. At Exemplary, we focus typically on the last 30 years of observations in order to characterize the climate for any given location. And we then present this data in a range of different formats, including TMY data, which is an internationally recognized standard format, the Energy Plus Weather, or EPW, which is a format made for the Energy Plus software, and the ACDB format, also known as Australian Climate Data Bank, which was developed by the CSIRO to support the residential modeling tools. Our work at Exemplary Energy is focused on transcribing the historic observation with a range of layers of quality assurance and backfilling, because, for example, for some locations, hourly data is not always available. And so sometimes it is only available on 3-hourly or even daily temporal resolutions. And so we developed a range of processes for estimating the full set of weather elements. And as I mentioned before, what we develop is a 30-year time series history of weather, and then we analyze that to characterize typical or extreme climate characteristics for each location. We also apply those end results to our own archetype models to produce benchmarking results that we call the Exemplary Weather and Energy Index, where we compare real-time results with the long-term average and with what is called HERSAT's future meteorological years data, which is an estimate of future climate going forward 30, 50, or 70 years. And we'll be talking about this a little bit later in the presentation. As I mentioned before, we provide this data in different formats for more than 250 locations in Australia, and these enhancements will support modelers to provide more reliable and timely results to aid the efficient design and management of both thermal and hydrothermal systems. One of the biggest challenges that we came across is the timely sourcing and dissemination of weather data. And as I said earlier, most of the raw data is available from the Bureau. But for some complex internal reasons, the Bureau stopped disseminating solar data in 2019. And so we have only recently recommenced providing the data because we established a number of short-term workarounds with some of our key partners. But this was just for a few capital cities across Australia. And more recently, we began purchasing the data from a commercial provider that is Solcast. Solcast's global solar database is produced using high-resolution imagery from a range of geostationary meteorological satellites. They utilize observations from the advanced imager on board the Mawari 8 satellite, and they disseminate the gridded solar data utilizing their in-house radiation model. So these real-time services has been successfully integrated into our product since May 2022, and it has allowed us to extend it to the 8 capital cities. For other less time-sensitive applications, we also use the BOM's terrestrial observations and their QA gridded solar data. And this allowed us to produce weather data time series in various formats to cover the period 1990 to 2021, and also create reference meteorological year, the RMY, climate data files for more than 250 locations. Moving over real-time data, the challenges coming from sourcing the data are obviously exacerbated in this case, but we have now entered a commercial agreement with the BOM, and so we are now able to extend the real-time data services to about these 200 and more locations in Australia on demand. But we already have them available to the public now for the 8 capital city, as I said before. The value of real-time data is that it can be applied to calibrated model, which enable detailed consideration of control parameters and evaluation of HVAC systems and overall building performance. For example, during building commissions, it becomes really important in understanding the specific relationship between the building consumption and the weather in a specific location, so that underperformance can be timely identified, which can then trigger restorative actions. Additionally, we at Exemplary produce and freely share what we call the Exemplary Weather and Energy Index for this purpose, which is a monthly service that we provide to the industry through our blog and our subscription email, Exemplary Advances. With this service, we aim to help users understand how recent weather compares to the long-term average, applying the real-time weather data and the reference meteorological year data to these 3 building archetypes, which are comply with the current NCC. And we simulate those into Energy Plus, and we also simulate a 5 kilowatt domestic PV systems. For the building simulations, we also apply what I described before as the ERSA's future meteorological years data to estimate the consumption also for the future climate going forward 30, 50, or 70 years. These are the archetypes, and they are a 3-story office building, a 10-story office building, and a ground-level supermarket. They were developed, including the HVAC systems, utilizing a technique that ensures that they will comply under the current building code in each of the 8 capital cities. And to summarize the 3 main applications of the Exemplary Weather and Energy Index, more broadly, the results can be used from current owners and managers as well as prospective owners for monitoring and predicting the energy performance of a building on a square meterage basis for benchmarking in Green Stars, MassCore, Naders, and Neighbors benchmarking programs. This here is some of the results that we propose with Exemplary Advances. This infographic is one of the visual tools that we use to communicate how the most recent month of data compares to the historic average. So for example, in Sydney in October, the temperature was on average just 0.3 degrees Celsius below the historic average, while relative humidity was significantly higher and the global horizontal irradiance was significantly lower. This is summarizing the weather index of the Exemplary Weather and Energy Index, while the results of the simulations of the 3 buildings archetypes in the solar PV systems make up for the energy indices, which present variation in heating and cooling across the three building archetypes, as well as the output utilizing our modeled PV system. To conclude, as in 2019, condensation minimum requirements were incorporated into the NCC and further enhanced in the NCC 2022, we are aiming to include precipitation into our datasets. While moisture control verification by simulating is already possible using accredited software such as WUFI, there are no reliable datasets which include precipitation in Australia in a recognized format and adequate temporal resolution. And furthermore, we also want to describe the X and Y's in precipitation in the same way we are characterizing X and Y's for building HVAC, which will be presented in another presentation tomorrow. And we're doing this in order to better understand moisture management under acute circumstances. One thing that is further justifying our work is that preliminary analysis of the data used by Laros Technologies, sourced from Medianorm, showed a wide variance in the data that is currently used for this purpose, as is shown in this table. And finally, while cloud cover data is already present in ACDB, TMY2, and EPW files, these values are often just estimated utilizing the satellite-derived solar data in the APSRC Clear Sky model. And to improve this, we are comparing different estimates of cloud cover, for example, manual observation, ceilometer observation, and clear sky inferred values, to provide more reliable cloud cover data for the whole range of weather and climate data services. Now, thank you so much for your time. There should be a few minutes available for Q&A, and Trevor will be answering your question. Thank you.